question is about the effect of mapping using the exponential function and what happens to straight lines. So let's start out by parameterizing the straight line L. The straight line L can be parameterized as a collection of all of the points of the form a plus b times t, where t is a real number, and a and b are complex numbers. So this is the complex version of something that is done in first year in vector calculus, where you in the study of vectors, where you parameterize straight lines in very much the same way, but using vectors rather than complex numbers. So, when is the straight line horizontal? L is horizontal when B is real. That's really what it boils down to. If B is real, then the BT is moving in the horizontal direction. If B is not real, then BT is moving in a non-horizontal direction. So here is our line, and we know when it's horizontal. Now, what can we say about f of L? Well, f of a plus bt is, of course, the exponential of a times the exponential of bt. And this basically is just a constant. This is not going to affect what happens very much. It may dilate things a little bit, it may rotate things a little bit, but if we have a straight line here, then if just this alone is giving a straight line, then this will also be a straight line, and if this is not a straight line, then this will not give a straight line. So I'm not going to worry about e to the a for a moment. So e to the bt could also be written as e to the real part of b times t times e to the I times the imaginary part of b times t. Now, if the imaginary part of b is non-zero, then this is something that is going to give us some rotation. And in fact, we'll see that it gives us a spiral of some sort, or perhaps a circle. This real part of b is just some real constant, and this is going to give us just a positive real number. So, if you like, this is the polar decomposition of this point. This is the r part, and this is the e to the I theta part. Now, there are several possibilities. This may be zero, this may be zero. We'd better make sure that b is non-zero, because otherwise we have a rather dull straight line. We only have a point, and that's really not to be considered. So we can't have both of these zero, but we might have both of them non-zero. So there are a range of possibilities. Let's consider the first possibility. If the real part of b is equal to 0, then this is just constantly 1, and as t varies, this goes around and around and around a circle. So we get the circle. Alternatively, if the imaginary part of b is equal to 0, then this is constantly 1, and e to the real part of b times t moves along a ray coming from the origin, and in this case, we get, when the imaginary part of b is equal to 0, we get a ray from the origin. In other words, we get a part of a straight line. Now, if neither of these is equal to 0, then we can really consider the imaginary part of b times t to be a number theta, and we will be able to express the r here in terms of that theta. And in that case, we end up with something of the form r is equal to e to the c times theta, where c is determined using these two things. And this, in polar coordinates, is the equation of a spiral. So in this case, we get a spiral. In particular, the only time that we get when the image of a straight line is a straight line, or more precisely part of the straight line, is when the line is horizontal. And that's the end of that.